Hi and welcome to this clip looking through your homework that was set on aromatics. So my intention was to connect this homework a bit to the learning aims from the class that we're talking about on the slides. So these have been summarised on the right hand side of the screen, so you need to be thinking about recognising key differences between aliphatic, alicyclic and aromatic. So recognition is fairly low level, but it should be possible to recognise things with prompting. That again moves on to recall, so that comes from flashcard work, making sure you can recall the key features of the benzene aromatic ring. Before we move on to grade B and grade A type challenges, which require you to start doing some application, which is why the word apply pops up there. So applying ideas and then applying knowledge to something familiar is how you get from B to A. So it's important to point out that they shouldn't be taken in isolation. They should be taken in sequence, starting at grade D and then moving up through the scale of the grades. So for example, if you happen to be able to apply knowledge of electrophilic substitution, but you weren't able to work out what aliphatic actually means compared to alicyclic and aromatic, you're still stuck at grade D, unfortunately. So it's important to make sure that all of them are looked at as a whole. So let's look at the first question. It asks us to think about a benzene molecule. So to do this question, you need to think about what a sigma bond actually is. So a sigma bond is the same as any normal single covalent bond. So if you draw the fully displayed formula of benzene, you need to draw it like what's on the screen there. So you've got your sigma bond between carbon atoms, but also the circle in the middle representing the pi system. So if you now consider how many single bonds you've got, so starting with the carbon to carbon single bonds, you obviously have 6. But if you also think about the carbon-hydrogen bonds, they're sigma bonds as well. So that means you've got a total of 12, which means it must be answer D. So moving on to the next one, it asks you to consider aromatic, unsaturated and alicyclic. So you've got to think about the definitions of these. So I'm not going to give them to you, I'm going to let you go and look them up, and you'll see that on the benzene ring, that obviously means it's aromatic, so that gets number 1 ticked off. So that means number C, or letter C, is going to be wrong. If you look at the ethyl group coming off, that's obviously going to be saturated. There's no carbon-carbon double bonds there, but it can be argued that the aromatic ring is unsaturated because the ratio of carbons to hydrogens doesn't involve complete quota of single bonds. So therefore, it's going to be aromatic and it's going to be unsaturated. So if we look at the two meanings of aromatic and unsaturated and apply them, you can see why it's going to be answer B. So what this question does is it further develops your understanding of the terms alicyclic, aromatic and aliphatic. If we look at the question carefully, you can see there's a highlighted piece of information there that suggests there might be some overlap between the 3 categories of compound. So this now allows us to think about these a little bit more fluidly. So in other words, one compound could go into more than one category. So any compound that doesn't have an aromatic ring in it automatically becomes aliphatic by default. Now within aliphatic compounds you've also got alicyclic. So if we bear in mind that alicyclic compounds are aliphatic compounds that also have a ring structure within them that isn't aromatic, that gives us E, H and J. So using that logic, that means there's only 2 compounds we haven't talked about yet, and they must fall outside these 2 categories that we've just described, so that must mean that they're aromatic. So that now gives us our classifications. So this final bit is an application question because it's asking you to convert a relatively simple idea, an alkyl group, into something that is not in the textbook. So it refers you to compound I. So to try and locate the alkyl group that they're talking about, you need to, first of all, isolate the longest carbon chain that also contains the CC double bond. So that now means that the CH3 must be our alkyl group they're talking about. Now because it's CH3 and the number of carbons is 1, so if N is 1, 2N plus 1 is going to give you 3, so it's CnH2n plus 1. So a little bit of deduction there. So this question is talking about two of the compounds, compound J and compound H, and it makes reference to the fact that compound H can be made by reacting compound J with an acid catalyst. So this is drawing on your recall of alkenes and alcohols from first year chemistry. So it's a dehydration reaction, obviously, using H3PO4. So to complete the equation, you need to put H2O in there, obviously, because it's dehydration. So the first thing they want is an equation for the reaction, but they want you to use molecular formulae. So if you were to write it in the way that I've just written it, it wouldn't actually get you any marks because you've been instructed to use molecular formulae. So the first thing to do is to convert that to molecular formulae. So that would be C6H12O, giving you C6H10 plus H2O. So then they want the percentage yield of compound H. So that's the actual moles over the theoretical moles times 100. Now we have to work out both of those values before we can get an answer. So the way to do that, obviously, is to do mass over MR. The MRs have now been worked out as 100 grams and 82 grams per mole, respectively. So a little word of warning. I've actually marked quite a few scripts before I did this video clip, so I can maybe put in a few sort of nuggets as I go along. I noticed that lots of people were making completely avoidable mistakes. So there's no excuses really for getting an MR wrong. All you do is count up the number of each element, and you've got a periodic table you can refer to. So there's no reason to get 100 grams or 82 grams wrong. So the next thing to do is to notice that there's a 1-to-1 mole ratio between the compounds. So let's do the actual moles first. So we've obtained 2.05 grams of compound H, and the compound H has a molecular mass of 82, so a molar mass of 82 I should say, so that gives us 0.025 moles. If we do the same thing for compound J, we end up with 0.0765. Now because it's a 1-to-1 mole ratio, you'd expect, in theory, 0.0765 moles of compound H. We only got 0.025 moles of compound H. So now we can see what goes where. So that gives us 32.7. Notice that the instruction finally was to do giving your answer to 1 decimal place. So this next part of the question is quite straightforward because that last part was a bit harder. So all you need to remember is a simple test that can be used to carry out or to confirm, the presence of the functional group in compound H, which is obviously the carbon-carbon double bond. So something along the lines of bromine water being discolorized is all you need for this one. So what you've got to do is take compound H and just put bromine onto the carbon-carbon double bond. So when it says draw the structure, you could have done it as a displayed formula, you could do it as a skeletal formula, or any combination thereof. So essentially, because it's not telling you to use molecular formulae, for example, like it did earlier on in the question, this time it gives you a bit of a break and says, look, just draw it any way you want, so long as it makes sense and it's not confusing. Okay, so let's now go on to the next question in the homework. So before we go anywhere with this question, it's interesting, isn't it? The first sentence says, this is likely to be an application question because it talks about salicylic acid. It also talks about medical compounds made from salicylic acid. So it's an application in real life. So they're asking you to talk about or think about stage 2. So they're also thinking about a particular mechanism that you should have come across before. So you may remember that this relates back to our learning aim at the beginning of the homework, which was to look at, for A grade, to look at unusual electrophiles and see if we can apply our ideas across. So it's telling you it's an electrophilic substitution. So it's saying to you, you can use the mechanism that you've learned from your flashcards, but just apply it to this particular electrophile. So what we've got to think about is, how does this CO2 molecule behave as an electrophile? So CO2 is neutral. So we know it's not going to have a positive charge on it in the sense of a full plus. But carbon and oxygen have different electronegativities. So that means you can put delta plus on one and delta minus on the other. So let's have a think about that. So I'm going to put the delta plus on the carbon, because the oxygen is definitely more electronegative than a carbon. And now I've got a species that can behave as an electrophile. So when you're deciding where to place the curly arrow, obviously pointing at the delta positive carbon, you need to be a bit careful and then decide, where am I going to place that curly arrow? So it can't just come out of anywhere on the ring, it has to come out of somewhere where the substitution is going to happen. So you need to make sure that it comes out at around sort of 1 or 2 o'clock, if we're talking about the positions on the clock face. So not down the bottom of the ring somewhere, up towards the top on the right hand side. So notice what's happened. C double bond O has become C single bond O with a negative charge on the oxygen. So the pi bond must have broken, and oxygen would pick up both electrons. So the intermediate is obviously going to be based on the normal kind of model that you've used for a partially delocalized pi system. So the open end of the partially delocalized pi system faces the point of substitution. The O minus is put at the side because that's not taking part in the reaction, but you must make sure you've got the curly arrow in there. Okay, so we now need to think about what type of reaction takes place during stage 1 and stage 3. So in stage 1, phenol loses H+, and in stage 3, the species C6H4COO- gains H+ on the O- and on the COO-. So 2 places, 2 substituents. So because we're getting a proton transfer, this has to mean it's a neutralization reaction. So provided we put both those points down, we get those 2 marks. Now, admittedly, that particular part of the question was quite hard. That was quite applied to think that through. So this whole question is actually quite demanding at the end of this piece of work. So let's now go on to the next page. So this next part is another percentage yield question, but just coming at it from a slightly different angle. I'm not going to go through it in quite the same way as I did before, because it's essentially the same mathematics. So what they want this time is the mass of phenol. So if we have a look at our original reaction scheme, and then look at the question, it says a chemist prepares 4.83 grams of salicylic acid from phenol, and the percentage yield of the reaction is 45.0%. So what we've got to do is convert the masses into moles. So we just have annotated the reaction scheme there, to tell you it's a 1-to-1 mole ratio. So the first thing to do is to work out the MRs of your phenol and your salicylic acid. So now I can work out the number of moles of phenol. So I've worked out that the number of moles of salicylic acid is 0.035. So I can assume that the number of moles of phenol is also going to be 0.035, as you can see that I've put underneath the reaction scheme. So assuming a 45% yield, this would actually require 0.0778 moles of phenol. So to get the mass of phenol, you multiply the moles of phenol that you'd need by the MR of phenol. So that means 7.31 grams. So this final bit was an extension question, but I'll just go through it really briefly with you. So it introduces ethanoic anhydride, which at the point at which this homework was set, you want to come across, but we'll do acid anhydrides later on in the second year. So it shows you what ethanoic anhydride is in skeletal form, and it tells you that aspirin can be prepared by reacting salicylic acid with ethanoic anhydride. So this was an optional question. I did say in the homework that you didn't have to do it, but if you did want to do it, to push yourself a bit beyond where you are right now, you would have needed to have gone and looked up an ester. Now, it sort of mentions it very subtly in passing, but it says aspirin is an ester of salicylic acid. So you can see from the structure top right of the page what salicylic acid actually is. It's got a COOH group. And we make esters by reacting a carboxylic acid, which salicylic acid clearly has, with either an alcohol, an acyl chloride, or an acid anhydride. Now, because ethanoic anhydride has the name anhydride in it, it must mean that it's an acid anhydride. But this isn't the only possibility. If you think about it, salicylic acid can also be classified as a phenol. And phenols can also form esters by losing an H plus from their OH group. So you can see the phenol functional group in salicylic acid can also react at the OH and not just at the COOH. So what's going on is that the ethanoic anhydride molecule breaks in two at the C single bond O single bond C, and that gives two molecules of ethanoic acid, one of which goes on to react with the phenol part of salicylic acid to make aspirin, and then the other one goes off and forms a spare side product of CH3COOH. So like it says, this particular question would have required some reading ahead. I wouldn't have expected that many people to give it a go, so well done if you did. And when you come back to this homework, perhaps in your revision, maybe 6 months from now down the course, you'll see the actual point of this question from an A-level perspective. Okay, so for now, thanks for listening, and hopefully the walkthrough has answered some of your questions and maybe generated some others to take to subject extensions, etc. So in the meantime, thanks for listening, and see you soon.